I would like to welcome Moshe Vardi from Rice University. Moshe has numerous awards, and I will mention just a very small number of them. So one objective recognition is that he is one of the top 40 most cited computer scientists. He got his PhD at the Hebrew University in Jerusalem in '81. He's been a Guggenheim Fellow, ACM Fellow, and a member of the National Academy of Engineering. And we are lucky to have him here because he stopped by on this campus to get a very nice award yesterday. So we are glad that he could also come and give a talk here. So,
thank you very much. Thank you very much. This kind of introduction reminds me of an apocryphal story about 3 students from MIT that published a paper. And the first one had a footnote next to his name, and it says AT&T fellow, received a fellowship from AT&T. The next one had a footnote next to his name, and it says Hertz fellow because he received a fellowship from the Hertz Foundation. The third one has a footnote next to his name, and it says a jolly good fellow. So I would like to tell you today about the logical revolution. And here is, I'm going to try to give you the whole story in one slide. If you go to skip after that, please stay awake from this slide. During the past 50 years, there has been extensive, continuous, and growing interaction between logic and computer science. In many respects, logic provides computer science with both a unifying foundational framework and a tool for modeling computational systems. In fact, logic has been called the calculus of computer science. The argument is logic plays a fundamental role in computer science, similar to that played by calculus in the physical sciences and traditional engineering disciplines. Indeed, logic plays an important role in areas of computer science as disparate as machine architecture, computer-aided design, programming languages, databases, artificial intelligence, algorithm, and computability and complexity. And this connection is really, if you think about it, somewhat surprising. On one hand, you have, go outside the college park, catch a person in the street, ask this person what is logic as a discipline, and if they are somewhat educated, they will say, oh, it's a small branch of philosophy. That's the best they would think about it. And to think that this small branch of philosophy is related to one of the most dynamic academic disciplines, it is surprising. Martin Davis, in a survey paper, Martin Davis is a prominent logician, in 1988 wrote in an article titled Influence of Mathematical Logic on Computer Science, wrote, when I was a student, even the topologists regarded mathematical logicians as living in outer space. Today, the connection between logic and computers are a matter of engineering practice at every level of computing organization. And the question is, why on earth do we have such a deep connection? And so, to answer that question, I will try to give a little bit of a background, and that really is the story of the story. So we have to go and ask us really a very fundamental question that people start only asking fairly late in the 19th century. What is really the fundamental method of physical sciences? What is not of science in general, but of physical sciences? There's something very unique about the physical sciences, that the way you do science is by constructing a mathematical model for physical reality. Right? Physicists use, chemists, they use mathematical models. Analyze these models, make prediction based on these models, then you go and you check these predictions against the physical reality, the experimental method. But this raises the questions, even more fundamental, what is a mathematical model? And people start asking this question in the 19th century, and they start asking even a better question, what is the language of mathematics? So people have been doing mathematics as we know it today since somewhere in the 6th century BC. What is really the language of mathematics? So the first attempt to answer this systematically is by Friedrich Ludwig Gottlob Frege in a small book called the Griffschrift, which means a language for concept, 1879, where it presents a universal mathematical language, which today we would call first order logic. And this would be part of the attempt to base mathematics on logic, and this is called logicism. And what Frege says that every mathematical discourse is always about some mathematical objects, numbers, geometrical objects, The relationship between them, we call them predicates. Operations on them, in arithmetics, we have plus, minus. Boolean operation, logical operation, and, or, not, implies, and quantifiers for all that exist, and maybe perhaps even other type of quantifiers. So, as an example, you can go back to the syllogism, where Aristotle says something like, all men are mortal, and to formalize it, we would say, more precisely, for all x, if x is a man, then x is mortal, and now we write it in the formalism developed in the 19th and 20th century, and we write inverted A for all, so it says for all x. If x is a man, we write man of x. Error implies mortal of x, x is mortal. Okay? So this is now we have a precise language to describe, for example, syllogisms. And the argument is that this language is a language in which we could describe properties of mathematical structure. So what is a mathematical structure? We talk about what is a mathematical model, what is a mathematical structure. So this again, people have tried to say what is general about all mathematical structure. And the answer is every mathematical structure has some domain, it's a set of objects, some relationships on them. And the relationship could be from binary or ternary or generally MRE relationships and functions. So domain, relations, function. This is what's universal about all mathematical structures. So take two examples. We'll take a graph. In a graph, the domain is a set of nodes, and we have one binary relation, and it's the edge relation. Okay? So this is, in this case, we have no function, only one binary relation. We can say something such as for all x there exist y, such as r of xy, okay, or e of xy, I should have written, e of xy, and I would say every node has an outgoing edge. For every node, there is another node and an edge to that node. Now let's take a similar structure, a group. A group is a set of elements, that's a domain, and we have one binary operation, there are no relation, but one binary operation, that's a product operation. And if a group, for example, is commutative, we can say for all x there exists y, such that x times y equal y times x. So we have a universal notion of what is a mathematical structure, and we have a universal language to talk about mathematical structures. So we are going to focus mostly in this talk. I want to use graph as my running example. So when we take first order logical graphs, you have first order variables, and they refer to the nodes of the graph. And you have atomic formulas, either there is an edge from x to y, this is e of xy, or equality. We always use equality as a built-in predicate. And by starting from these atomic formulas, using the Boolean connective and or not implies and quantifiers, we can generate formulas. So here is a formula that says that the node x has at least two distinct neighbors. So the formula says there exists y and z, and there are different not, this little squiggle is not y equals z, and this wedge is and, there is an edge from x to y, and an edge from x to z. Okay, so there are two nodes, and there are edges from x to these two nodes, so x has at least two distinct neighbors. Here x is a generic node, we say x is free, it talks about some node x, we don't know yet what is this node x. So if I want to say, is this formula true in a graph, it doesn't make sense until you tell me who x is. You have to bind x. X is a formal parameter here. You have to bind it to a concrete element before you can say, is this formula true or not. So by itself, it doesn't make sense to talk about true. So we usually we write it like this. Take a graph G, and the binding alpha, and the formula, and this double turn style says truth, or holds, or satisfies. Now here is another formula. This formula says for all x, for every node x, there exists y and z, and they are distinct, and there are edges to x and z. So this says that every node has at least two distinct neighbors, and this one has no free variables. It talks about properties of all nodes in the graph. So now you can say, does it hold for a given graph or not? You can talk about the graph that satisfies this property, and a graph that does not satisfy that property. Now, In mathematical logic, we're typically interested in sentences because we want to describe properties of structures. Now, to build sentences, syntactically, you have to have formulas, and you have to have first formulas. Formulas are kind of a nuisance. They are necessary things that you build before you get to sentences, but you're only interested in sentences. And we will see in computer science we have changed this relationship. So these were the foundations, mathematical foundations or logical foundations of mathematics. They all have been laid late in the 19th century. And then in mathematical logic, the 20th century started on June 16, 1902. Because on that day, Bertrand Russell writes a letter to Frege. And the letter starts very nicely. Russell writes, I find myself in agreement with you in all essentials. I find in your work discussion, distinction, definition that one seeks in vain in the work of other logicians. Of course, Frege reads it and he's pretty pleased with himself. And then he keeps reading and he gets to the point where Russell says, there's just one point where I've encountered a difficulty. That difficulty ended up being such a severe difficulty that when Frege's book came out the next year, he ended in the appendix, there's nothing worse that can happen to a scientist than to have the foundation collapse just as the work is finished. I have been placed in this position by a letter from Mr. Bertrand Russell. So Russell pointed out, described what we call Russell's paradox, which was a contradiction in Frege's system. So Frege's system was inconsistent, it was contradictory. And for Frege, this was, his life was shattered by this discovery. That what he has done for the past 30 years is really logically inconsistent. And that inconsistency became known as the foundational crisis, because what Russell has identified is a paradox at the very heart of mathematics, in the very foundation of mathematics. This became known as the foundational crisis. You discover you build mathematics, and then you discover that the termites have eaten the foundation, and we don't have foundations. And the premier, the foremost mathematician of the time, David Hilbert, took on himself to solve this crisis. So this led to launching of Hilbert's program. Hilbert's program became known after, he didn't name it this way, but that's how people named it. It has 3 points. First of all, he wanted to solve the crisis, that is to show, you want to show that mathematics is consistent, and of course you want to prove it mathematically, the mathematics is consistent. But he became more ambitious, he wanted to show that mathematics is complete, you can in principle solve all questions in mathematics. And finally, and this is in fact where computer science was born, so to speak, he wanted to show that mathematics was decidable. There's a mechanical way to determine truth of every mathematical statement. Very ambitious program, didn't last very long, because by 1930 it was demolished first by Gödel, who demolished the first 2 points, and this is the Gödel first and second incompleteness theorem. So first of all, Gödel proved that even in arithmetic, there's no systematic way of answering all arithmetical questions, all theory of number theory, and from this it follows you cannot prove mathematically the consistency of arithmetic. So we don't even know whether pan arithmetic is consistent. And again, Gödel did it by this famous sentence, what's called the Gödelian sentence, that says, I am not provable. So this sentence, which is true, but not provable. And a few years later, Church and Turing, using similar ideas of diagonalization, proved that first order logic is unsolvable. There is no mechanical way of determining the truth of all potential first order sentences. And this question, which will become, I'll focus now, this question, what we call the decision problem. This was the 3rd point of Hilbert's program. This became known as Einstein-Lux problem, the decision problem. And it was formally posed in Hilbert and Ackermann published their first book on mathematical logic in 1928. And they posed the question, decide if a given first order sentence is valid, always true, or I will actually look at the dual, possibly true, which is satisfiable. Can you make it true? Is there some structure in which it is true? And this was shown independently by Church and Turing, with Church beating Turing by a few months, that this question is undecidable. And we are mostly familiar with Turing's proof these days, because Turing, to that end, to prove undecidability, you have to define what does it mean to be decidable? We have some notion of computability, and for that we introduced Turing machines. And as if you may know that last year was the Turing centenary, his 100th anniversary, 100th birthday, and there was lots and lots of events over this. This paper was from 1936, and he proved that the termination problem, the halting problem, is undecidable. And again, you do it by diagonalization. You basically construct a machine terminates if and only if it does not terminate. If you could solve the termination problem. And then he reduced termination to the decision problem. So that's how you prove the decision problem is undecidable. So this was important foundational questions. What we got out of it in computer science is a computational model, but for logic this was a severe blow. It means that there is no mechanical way of determining truth in logic. So if you look where logic stands in 1936, it was proposed as foundations for mathematics, but it's incomplete, and it took many years before people find out not only Gödelian sentences, but even very concrete theorems, such as the continuum hypothesis does not follow from the axiom of set theory. It cannot prove its own consistency. It has an unsolvable decision problem. Even the simplest questions about computation, termination, is unsolvable. So things are looking pretty grim. So one question is, can we get some positive results? And typically what mathematicians do when the general everything is impossible, you lower your aim, you try to go for special cases. Maybe we can prove decidability for some important special cases. So one attempt to do it is by looking at fragments. Let's look at fragments of first order logic. And so maybe the whole logic is undecidable, but maybe we can find useful fragments that are decidable, so we can do something with it. So for one example of a fragment that is decidable is the monadic class. So the monadic class is first order logic with monadic predicates only. So before we saw, for example, we used the edge predicate. Edge predicate is a binary predicate. But if you only want to do syllogism, for example, then you can do it with monadic predicate. So you can write something such as, this is a very simple syllogism. If it is true that for all x p of x, and for all x p of x implies q of x, it then follows, this also means it follows that for all x q of x. So if x is always in P, and every x in P is also in Q, then every x must be in Q. And in 1915, Leopold Lovenheim showed that this is decidable, and the way he proved this is decidable is by proving that if you're given a sentence, if it has any model, that model, we can bound the side of the model as a function of the side of the length of the sentence. So once you're given a sentence, you have a bound on possible models, you can just enumerate them and then check them one by one to see whether this is true. And we really cannot do much better than that, and use a technique called quantifier elimination, which means that the thing that makes first order logic powerful are the quantifiers. If you can somehow get rid of them, perhaps paying some blow-up, we can reduce it to propositional logic, and we know how to solve propositional logic. So this was an important decidability result, except that this is just monadic logic. We cannot even talk about graphs. All we can do are syllogisms, or as Lewis Carroll called them, syllogisms. What other things are decidable? So it took until 1983 to finish the classification project. Okay? This took like 70 years to do it. And what have we been able to do? The Bernay-Schoenfeld class, so sentences that have exist and then for all, we call it E star A star, exist, one universal, and then string of exist, that's called the Ackermann class, and without equality, if you have exist star, two universal, and then exist. That's it. In fact, even here, once you have equality, this is what took many years to prove. If you have equality, this is undecidable. These are, when you look at this, these are very, very limited classes. So we've got some decidability, but these are all incredibly weak classes, so undecidability creeps in very, very fast. As soon as you have any kind of expressive power, bam, it's undecidable. So this in some sense you could say that the fragment classification project is a failure in the sense we didn't find really anything very interesting that we can use. There are very few applications where you can use these fragments. So perhaps focusing on syntax is the wrong thing to do. Perhaps instead we should focus on interesting mathematical domains. So we know that arithmetic is undecidable. So if you have plus n times, this is undecidable. Let's try to do only plus. Okay? What is it? Third grade mathematics. I don't know when you do product. I think maybe fourth grade. So we'll stick in third grade. So we'll take very simple structure. The natural numbers, equality, and plus. Turns out you can do quite a lot. You know, I can say that y equal 2x, so I can have constant product by writing y equal x plus x. I can define that x is 0 by saying that for all y, either y is equal to x or y is greater than x. That means x must be 0. Then I can say that x is less than y. I can say that x equal 1, and so on and so forth. So it turns out I can really do all what we call integer programming or integer inequalities with quantifier. It's a fairly powerful theory. So here, at least about addition, we can say very powerful things. And then in 1921, Moses, which is Moshe, which is my namesake, Pressburger, proved decidability. In fact, he proved, he gives a sound and complete axiomatization, and he proved that this is decidable. And he uses a quantifier elimination. And if you use quantifier elimination, at the end you just need to reason about arithmetical congruences. Today we actually typically use a new proof. There is a very nice elementary proof to use automata theoretic techniques. So the theory is decidable. So now we can start to get some excited, because now we have a non-trivial theory. It's about a rich mathematical structure, addition, and this theory is decidable. So this is very nice, until in the 70s, people start looking at, there is a new notion on the block, there's a new kid on the block, and this kid is called complexity theory. Now it's not enough to say decidable or undecidable, you want to know what's the complexity. So this problem that was remember, decidability is 1929. So now, about 50 years later, finally we ask the question, what about complexity? And Open shows that this is decidable in triply exponential time. And then Fisher and Rabin, in one of the first non-trivial lower bounds, proved that there is a doubly exponential lower bound to this. So in 1974, Rabin has a paper in the IFIC proceeding. This was the time there was this big conference for all of computer science, and it's a paper called Theoretical Impediment to Artificial Intelligence. And in a very understated way, he says the complexity results point to a need for careful examination of the goals and methods in AI. Essentially, he's saying this is at least doubly exponential. That means that even reasoning about addition is practically infeasible. How can we hope to have any kind of artificial intelligence if the simplest problem, addition, is already doubly exponential? So, another bust. Yes, with decidability, but it's not clear it's any good. Another attempt was to go and to reason about, not about addition, but something which is more maybe computer science, to reason about words. Very simple structure, right? Words. So let me first of all remind you a little bit background in automata theory. We have, this is NFA, non-deterministic finite automata in one slide, right? So I have here what is an automaton. You have finite alphabet, finite set of states, a set of initial states, a non-deterministic transition function, and a set of accepting states, right? This is the model that you teach in the most fundamental course in automata theory. And here is the example. You have an automaton, and you enter on the left, and 0 tells you always to the left, and 1 takes you always to the right, and you accept the red circle. So when you accept on the right. So this automaton defines all the words that end with 1. Okay? I hope that everybody is familiar with that. So in the late 50s, people realized that a mathematical, just like anything is a mathematical structure, a word is a mathematical structure. What is, remember, mathematical structure, you have to have domain, relation functions. Here the domain is the set of positions. So if it's a word of length n, then the domain is the number 0 to n minus 1. I have one dyadic predicate comparing position, which position is to the left of what position. And I have one monadic predicate telling me what letter is written in every position. So P sub A is true whenever the letter A is written there. And so now I can write sentences about words. For example, here is a sentence. It says for all x, there exists x. That's it, for all y, not x less than y. And this says that x must be the rightmost position, because nothing is to its right. And the last letter is 1. So this says that this ends with 1. So the same thing we did before with an automaton, now I can do with a sentence. The sentence says this word has 1 in the rightmost position. And so we see that you can describe the same property using automata and using logic. And indeed, this became a very fundamental result in the late 50s. This is called the Cauchy-Elgot-Trachtenberg theorem. And he said that those two very different looking formalisms, on one hand, monadic second order logic. Monadic second order logic is a logic where I added here, you can even quantify over sets of positions. So this is not first order, you quantify over position. I'm allowing you to quantify over sets of positions, even more powerful. And this is equivalent to NFA. And was defined a class of regular languages. So this is another indication that this class is a very robust class. And the translation is effective. They show you how to go from NFA to MSO. You give me an automaton, I'll give you the sentence in logic. You give me a sentence in logic, I'll give you the automaton to do it. There is an interesting tidbit of history here that I cannot figure out. So I ask, and every time I give this talk, I ask the question. Bush and Elgot wrote a joint abstract and 2 separate full papers. So there must have been some very nasty fight there, but I cannot get the details on it. So anybody knows, please let me know. So why is it useful to have this equivalence between logic and automata? So what is the most fundamental decision problem in automata theory? Given an automaton, does it describe anything interesting? That is to say, is the language that it describes, is it non-empty? Automaton describes the empty language is not very interesting, so this is the non-emptiness problem. And it's not very hard to show that in order to do it, you just need to reason about the underlying graph. What is the underlying graph? The set of nodes are the states of the automaton, and you have an edge. You have an edge from S to T, if it's possible to go from S to T upon reading some letter. If there is a transition from S to T reading some letter, we don't care about the letter, we say there is an edge from S to T. And a very easy lemma that you can all prove just by 2 minutes of reflection, the automaton is non-empty even only if there is a path in this graph from initial to accepting state. There must be a way to start from initial state and walk your way to an accepting state. And so this is just graph reachability. So we can solve it in linear time using any kind of graph theoretic algorithm. Right? This is the most fundamental question in graph theory, graph reachability, very easy problem. So the non-emptiness problem is decidable in linear time. Now, what is the analogous problem in logic? Given a sentence, does it have any model? It's a satisfiability problem. On the face of it, it's not clear. You give me a second order logic, how do I even attack the problem? But the equivalence gives us effective algorithm. We know that the sentence is satisfiable even only if the automaton is non-empty. So this is algorithm. Start from the logic, translate to automata, and then check for non-emptiness. We already know that this step here is linear in the size of the automaton. So the question is, what is the complexity of this stage, of this translation? This translation is by induction on the structure of the sentence. Many proofs in logic are by induction on the structure of the sentence. And every step is potentially exponential. So as a result, we get a tower of exponential, and the height of the tower is by itself unbounded. This is of linear height. This we call non-elementary, we call it. Okay? If it was just octuply exponential, oh, this is okay, this is elementary. It's this unbounded tower of exponential that really think, oh, this is really horrible. And it turns out, this was proved in 1984 by Larry Stockmeyer, you cannot do better than that. Okay? You can prove a long bound, there is no bounded height tower. Now, in case you don't believe me that this function goes very fast, let's calculate it. Okay? 2 to the 2, no problem, it's 4. 2 to the 2 to the 2. 2 to the 2 to the 3. Nah, 256. 2 to the 4, only 4 billion. Okay? 2 to the 5. Well, excuse me if I didn't calculate it precisely, but it is roughly 10 to the 10 to the 9. Okay? Now this is not an astronomical number. It's a maybe cosmological number. Okay? You take the known universe, but let's say 14 billion light year, think of it as one big sphere, and pack it with gates the size of Planck constant, which is I think something like 10 to the minus 35 meters, and you're not even starting to approach this number. Okay? So these are very large numbers. So we have a beautiful theory. This is the monadic theory of worlds, beautiful decidability result, nice connection with logic and automata, complexity, horrible. But we really could have done earlier what is the most fundamental logic? It's Boolean logic, right? So we can go back to the 19th century again, and Boole realizes that you can go back to the syllogism and you start thinking about them algebraically. It's all about sets of objects, and you can manipulate them algebraically. And here is a paragraph from his book. He writes, if an adjective is good is employed as term of description, let us represent by letter as y all things to which the description good is applicable, i.e. all good things, or the class of good things. Let it further be agreed that by the combination x times y, here I'm using algebraic convention that juxtaposition means multiplication, x times y, shall be represented that class of things to which the name or description represented by x and y are simultaneously applicable. Thus, if x alone stands for white things and y for sheep, let xy stand for white sheep. xy, x times y. So he's saying logical conjunction is a product operation in the proper Boolean algebra. And so the question that comes out of it is Boolean sum. Given a Boolean expression using n or nots, is there some way to assign zeros and ones so the whole thing comes out to be true? So here is an example of a formula, right? It's a conjunction of 3 disjunction, and here's an assignment that will make it true. And how do you know that? Well, you just have to plug it in to see that it makes it true. But if you try to satisfy it, you really don't have anything which is much better than just try all possibilities. So people realized very early on that this seemed to be a difficult problem, deciding Boolean satisfiability. William Stanley Jevons, right, who followed Boole, wrote, I have given much attention, therefore, to lessening both the manual and the mental labor of the process. And I shall describe several devices which may be adopted for saving trouble and risk of mistake. So in fact, he built what's called a logic machine, some logical contraption that can try to solve this problem for very small number. He did it for 4 propositions. 4 propositions in the state space of 2 to the 4 is 16. It's not difficult, but he did it with moving wooden pieces, so it's not trivial. Ernest Schroeder, getting a handle on the consequences of any premises, or at least the fastest method for obtaining these consequences, seemed to me to be one of the noblest, if not the ultimate goal of mathematics and logic. So Schroeder says solving Boolean satisfiability is the problem of mathematics. And in fact, in the early 50s and early 60s, especially in the Soviet Union, people discovered that this is one instance of the problem of exhaustive search. In Russia, there is one nice word for exhaustive search, parabol, and they tried to prove that these problems are really hard. They have made no progress until in the early 70s, finally Cook and Levin independently proved that this is NP-complete. Okay. So the theory of NP-completeness gave us some indication that it's a really hard problem. And so very quickly, just to remind all of you, so NP are the problems where if you give me a candidate solution, I can check it efficiently. So if I want to find a Hamiltonian cycle in a graph, we don't know how to do it efficiently, but you give me a candidate, I can very easily check that it's a Hamiltonian cycle. We don't know how to factor numbers efficiently. Problems are really hard not only in the worst case. In the worst case, a meteor is going to hit us in 5 minutes and we're all going to be dead. Okay, that's the worst case. Most of us don't seem to lose sleep over this possibility. In fact, by quantum theory, you could just evaporate in the next minute into nothingness, right? That can be happen. That's quantum fluctuation, right? Your self will interact with your anti-self and it will disappear. And we don't seem to be worried. And we don't have a good theory to say when should we be worried really. And I want to finish with one of my favorite authors, Blaise Pascal, who is also, of course, you know about him as a mathematician, but he's also a very famous French writer. And he has two beautiful quotes about logic that I like very much. Two excesses, to exclude reason, to admit nothing but reason. And even the better one, the heart has its reasons, which reason knows not. Thank you very much.
Questions, please. You answered all the questions you preempted. Sure, no questions, please.
So it seems that the next frontier then should be the neural incompleteness theorems, which are not only are about complexity but about impossibility. So do you see anything, or I guess the Terminator work in some sense is nibbles at turning undecidability into something practical. Do you have any other examples that you're aware of that you can?
So this is still a matter of the practical significance of Gödel incompleteness is still a matter of debate, so to speak. So we do have the beginning. People say, "Oh, these are just crazy sentences. I'm not proven. Nobody cares about such sentences, right?" But then we discover the continuum hypothesis, which we know does not follow from the axiom of set theory, and these questions of, in set theory, people are still spending an enormous amount of time trying to understand what extra actions do you need to settle this. And then there is people say, yeah, but we cannot think of any theorem in arithmetics. And then Paris and Harrington came up with some kind of a Ramsey property that does not follow from binary arithmetics. So I would say that for people to do foundational mathematics, this is still very much a question, which is, how relevant is Gödel theorem to practical mathematics? The answer is that most practical mathematicians proceed with their daily work, not losing, right, even 2 minutes of sleep over incompleteness. I mean, just very hard to point out, to find that here's a problem mathematicians have been working on. It's a standard mathematical questions, whatever, and the problem is an ill-defined term, but it's a standard mathematical questions, and we discover later on this is not determined by the axiom of mathematics. Very, very few such theorems. There are some theorems that, again, they are in discrete set theory, there's such problem. But most mathematicians really couldn't care less. That's the reality. So they say, okay, it's a problem in principle, but not in practice.
Do you think the rather big picture when it came from P versus NP, isn't it perhaps because you're asking for too much? In the sense that you're asking really for a worst case scenario.
So there have been, so I think there is a growing realization in computer science that worst case complexity is not a very good measure. It's a good measure when you have something positive. If you have an algorithm that's always quadratic, this is wonderful, okay? But just because something in the worst case can be exponential, that doesn't tell you much. And there have been some attempts to try to develop better measures. For example, people try to describe, there's been some work on average case complexity. That has not been, it's a deep theory, but it has not been very successful in practice. So if you look at most of the work people publish and typically talk about, here's the worst case complexity of my algorithm. People continue to prove worst case lower bounds. I've done it myself many, many times. It's like Mark Twain and smoking, right? I've done it myself many, many times. It gives you, I can't say it doesn't give you anything, it's a challenge, but what you cannot do, we now understand, look at the problem and say, oh, this is exponential, this is double exponential, this is triple exponential, and therefore say, oh, it follows, this is infeasible in practice. That simply does not follow. That's what we learn. And I think that, do we have better notion of complexity theory? This is now emerging as it's a nascent area of research to try to understand. For example, it's very easy to write Boolean formulas with only hundreds of variables that you cannot solve using any existing tool. On the other hand, we can solve very large problems. We don't understand what makes a problem hard, what makes it easy. So I think there is a room here for some very fundamental theory.
So I've been doing databases for about 3 decades now from a more, I'd say, a practical viewpoint. So one of the things that occurred to me was, when I was starting as a grad student, or even along this way, how much of this talk would have made sense to me? Now, it makes sense, but just for somebody starting off, it's also nice because I think there's things when I teach about databases and so on, I can point to, well, it's from the 1600s, so we can't change it. So this was really nice to listen to a talk like this. I think it gives me a much better sense of the big picture and why things are. From a slightly different question, so I was expecting you to be talking a little bit more about things like the closed world assumption and non-monotonic reasoning. I think people like Jack and so on have been working here a lot in that. Can you tie it into, I like the way you were cleanly not going into some of the details. Can you tie some of this in to some of these things that many of us know about?
So I think that probably, and again, I'm not following very closely non-monotonic reasoning, but I think the biggest success in monotonic reasoning has been what's called answer set programming. And where people have, by now, doing probably about 20 years of taking one particular version, stable model, I think it's stable model semantic, taking down, the problem there are too many different semantics. But people say, let's focus on one, let's work with one, and continue to do it, using it as a descriptive formalism, developing algorithms to do it. It's exponential in the worst case, but they actually are able to show broader and broader applicability. They build tools, there are tools to do that. So I think that I could have very easily used answer set programming as another example for something that looks infeasible at the beginning, and it's easy to dismiss it, and after just a lot of effort in engineering and heuristics, we actually have today a system that can actually, I think it's another success story. I don't think it yet has broad recognition and applicability as SAT, but I think I can definitely say that out of non-monotonic reasoning, one very concrete success that I know about. There are many failures along the way, right? When you have in the war, you have to take over the hill. You have several casualties along the way, right? Most of what we do, right? It's a very sobering realization. Most of what we do as scientists will be completely forgotten and will have no value. History is very cruel judge, but it's enough to have a few successes, and these successes will really move science along.
What, if you don't mind my asking, what are you personally excited about going forward for the next, right now or in the future?
So I find this. I find I've been liberated, right? I've been imprisoned for all these years by this worst case complexity, right? You prove the log bound and then, damn, don't even go there. And suddenly it's a very liberating feeling. Wow. We can actually try to do this, right? So I think we can go back and revisit all kinds of things we just given up because we say, oh, it's undecidable, it's NP complete, it's X time complete. We go back and say, wait a minute, this is important. What can we do there? I think this gives us enormous opportunity to go back and look at hard problems that we thought were hard and we thought they were hard. So wait a minute, are they really hard? I think this is tremendously liberating. I would say, I'm out of prison. I'm out of prison of the worst case complexity. Okay, thank you very much.